Alright, silly people, here's the situation. For this guy, we're going to be solving this equation for the ground state of the harmonic oscillator to 5 significant digits um, by the wag the dog method. And Griffiths suggests that we use Mathematica for this, but we use Python in this house, so that's what we're going to use. And I already wrote the equation up here. And usually in Python, the strategy is to turn any arbitrary ordinary differential equation into a first order differential equation by defining a new variable, which is the derivative of your first thing. So if we define the variable chi to be the derivative of psi with respect to xi, then we can rewrite the equation like this: d chi d xi equals, and then I've just distributed the stuff in the parentheses out, so it's xi squared psi minus k psi, right? So to do this, we're going to need some packages. We're going to need numpy, right? And we're going to need matplotlib as well, because I do want to plot what the wave function looks like as we go. Plot as plt, if I could type, that'd be nice. And also we're going to need from scipy.integrate the solve underscore IVP function, which is what we're going to use to solve the ordinary differential equation, right? So the structure of this is pretty specific to the problem. So we're going to define, I'm going to do everything that is like the initial conditions first and then write the ODE function. So it wants us to do this on the domain of 0 to 10. So I'm going to say A equals 0, B equals 0, keeping to, or B equals 10, keeping to Griffiths notation. And we don't need C and D because that's just going to be the upper limit and lower limit of the plot. We're going to create an input list, which I'm going to call chi-ls because it is representing like the domain here. It's going to be a linspace object from 0 to 10 with 1,000 points. And we're going to create a variable k. Griffiths suggests we use 0.9 first, but then, wag the dog to see what the actual solution is. Also, we're going to need, I think that might be it actually. Yeah, that's what we're going to do for now. Now we can define the ordinary differential equation. It's going to be a function of xi and an input variable y, which is actually going to be an array which contains psi and chi. So we're going to, first of all, unpack the input array into its relevant components here. And we're going to write the differential equation now. So d chi d xi is going to be equal to xi squared, and it's times psi. So let me write times psi here. And it's subtracted by k times psi. And then we will have it return the new value of chi as well as the new value of d chi d xi to change chi and c as we go. So I'm going to create a variable called sol, which is going to store the solution of the ordinary differential equation. This is when we're going to call the solve IVP function. As the first argument, it takes the function, so ODE is what we've called it. Its second argument is the domain on which you want to solve it. We're solving it on the interval a to b. Then it wants the initial conditions for psi and chi. So Griffiths says set the initial psi to 1, so 1 here, and then set the initial d psi d xi to 0, so 0 here. And then The next argument is the integration method for the ODE. We're going to use RK45 because I think it's the best one. And we're also going to, now we have to put in like the input array that we want to plot it on. So this is where xi_ls will pop up. But yeah, after we've solved it, we can have it plot the solution's time axis versus the solution to psi, and we can show it off. So let's see what happens with this value of k. And you can see that the tail of the wave function is going to go to infinity for large c, which is kind of crazy. Then the next thing that Griffiths wants us to try is k equals 1.1. Let's give that a go. 1.1. Now the tail flips the other way, so now it's going to negative infinity, where c is large. What we're going to look for is we're going to try and hone in on the value of k that makes it so that it just goes to 0 at some point and flattens out to 5 significant figures. So I'm going to also change the range in which it shows the plot, like Griffiths suggests. I'm just going to change it from minus 0.25 to 1. That way we'll be able to see the crossover behavior. Obviously it's still diverging negatively, but here let's try plugging in 1 instead. It's still going negative pretty much, so let's add another significant figure. Let's go 0.95. Now it's going up again. Let's increase it. Still going up. Let's increase it. Still going up. Let's increase it. Still going up. Let's increase it. Okay, let's add another digit. Still going up. Let's bump it up a little bit. And again. And again. And again. Looks like it's 0.999 something. Let's add another digit. And bump it up again. 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 Okay, that looks kind of cool. Add another digit. It's still going up at large C. Now it's negatively diverging again. So obviously 0.99995 was the way to go. And that is already at 5 significant figures. So I think that's what Griffiths was trying to get us to do. So this is going to be the value for capital K. So nice.